Hey, so welcome everyone to another TCS Plus talk. Today we're very lucky to have Paul Gölz, who will tell us about algorithmic democracy. So now before we get started, there's just a few things I wanted to say. So first of all, the talk is being recorded, so we'll post it on our YouTube website. But I do want to encourage everyone to keep their cameras on. It gives Paul as much visual feedback as possible. And basically feel free to unmute yourself and ask any questions during the talk. But there will be a non-recorded session where we can just hang out and ask Paul any follow-up questions or anything that can come up. So I think that's pretty much it. Oh, let me thank the rest of the organizers. So there's a big team at TCS Plus. That includes Clement Canon, Rachel Cummings, Anindya Day, Sumega Garg, Gadam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens-Davidowitz, Tomas Vidik, and David Weiss. But with that, please, Paul, take it away.
Yeah, thank you so much, Eric. And hi, everyone. My name is Paul Gölz, and I'm currently finishing up a postdoc at Harvard. I'll spend much of the next year doing different postdocs in Berkeley, and after that, I'll be joining Cornell as faculty. And I really like this name of algorithmic democracy, so I've even put it in the title. But the community that I'm part of typically identifies itself under the name of computational social choice. This talk is a survey talk about some of the recent developments there. So let me maybe start by giving you a bit of an overview over what this area is about. Computational social choice arose out of an earlier strain of research, which is just called social choice theory, or social choice. And social choice theory has been home in economics departments and political science departments for much of the 20th century, where, in my mind, the central question is doing mathematics on democratic processes, and in particular voting. So the really central question is what algorithms you should use that take in a set of votes and produce an outcome as their output. So in this case here, the votes indicate preferences over possible outcomes. In this case, it seems that there's a choice to be made between a blue candidate, a red candidate, and a green candidate. And the algorithm has to take all of this in and then produce one specific decision. In this case, the blue candidate seems to make the cut. And this voting rule, which is what this algorithm is called, trying to figure out what makes a good voting rule and what these voting rules should satisfy. That is the central question of social choice theory. There has been a lot of renewed activity in social choice theory from the 2000s on, because that is when computer scientists entered into the area and built what is now the field of computational social choice. We still study the same kinds of fundamental questions and objects, but our common background in computer science has really informed how we approach these problems in different ways. So for example, of course, from computer science, we bring certain techniques where, for example, social choice theory traditionally looks at particularly simple voting rules. For us, the entire toolbox of algorithm design is fair game. So for example, one of the changes that you see is that we're considering much more complicated voting rules at times. Another point is that we have different approaches that are also informed by computer science. There are some ways in which this background is shaping our work quite profoundly, but because I want to be quick here, let me give some very superficial points. Where, for example, of course, we're much more interested in whether these voting rules are polynomial time than the economists and political scientists, where whenever we want to give guarantees, but we can't satisfy them, approximation is something that's very close at hand, which of course has many precursors in computer science. And then finally, we've also expanded into other settings. And in general, we've just expanded the kinds of settings that are fair game to study in computational social choice. But in particular, we've been interested whenever these settings mirror some other parts of computer science. So for example, voting on graph structures is very popular. Or one thing that we'll see today, voting where the outcome space is the space of solutions to a knapsack problem. The field of computational social choice is doing well, and it's very alive and vivid. And so here is just a random collection of topics of recent lines of work that stood out in my mind and that came to my mind. Some of these topics have actually been in better contact with the TCS community already over the last time. So for example, metric distortion, a big result of theirs by Katselis et al. Was actually at Fox 3 years ago. The subfield of fair division has a lot of personal overlap with the TCS community. But today I want to focus on two other topics that I think haven't yet had enough exposure to TCS. These two topics being participatory budgeting and finding representative panels. Both of these are topics that are close to my heart because I think that they have nice mathematical problems, but at the same time, they also have connections to points that really have impact in practice right now. And that is exactly the kind of mathematical problems that I like most, ones where you can prove something and then change something in the real world. I hope that you'll see some of that, even though I'll be focusing much more on the mathematics rather than the impact. So without further ado, let me enter into the first part of this talk on participatory budgeting. Participatory budgeting is a relatively new form of democratic participation, which typically happens at the city level. And it means that some part of the city budget is not just being spent by politicians, but instead the residents themselves get to decide what gets funded from this budget by voting. So here this is illustrated in a rather beautiful way. I suppose that the projects being considered here are painting this wall to make it prettier, or maybe buying some books for the local library, and maybe building a food pantry over there. And those are different projects, all of them cost money, and what exactly makes the cut and gets funded is decided by the residents. Participatory budgeting arose in the Brazilian city of Porto Alegre in the 1980s and was so successful there that it has since spread to 1,500 cities around the globe. And in some cases, really serious money is being spent. For example, in the city of Paris, for many years, the yearly participatory budget was at 100 million euros. But despite this prevalence of participatory budgeting, and despite the high financial stakes, we're far from a consensus about how the participatory budgeting should actually work. How should you actually translate people's preferences for what to fund into a decision of what gets funded? And that, of course, is a wonderful question for computational social choice. Let me make this more concrete by introducing some notation. So let's say that the city has set aside a budget, which better be a positive number B of dollars. And we have a set of projects where each project, so the set is called capital M, and each project alpha in M is associated with a certain cost, C alpha, which is, again, a positive amount of dollars they would cost to realize this project. Finally, we have a set of agents, of voters. So this is a set capital N, whose cardinality we denote by lowercase n. And of course, these voters have a preference over which of the projects we should realize. And throughout this talk, I will assume that these preferences are given as so-called approval ballots, which means that every agent I in N gives us a subset AI of the projects. Those are the projects that they approve, that they want to see realized, and they don't particularly care about the other ones. Of course, you could think of different ways in which the agents might indicate their preferences. For example, they might rank the projects by their value, or they might distribute points among them. And while both of these have also been tried in practice, these approval ballots are the most common form, and much of the theory has been built around this. This is what describes an instance of participatory budgeting. And the remaining thing, of course, is the voting rule, which is an algorithm that takes in all of this information and then returns an outcome W, when outcome W is simply a subset of the projects that have to fit into the knapsack. So if we sum up the costs of all the projects alpha in W, that has to come out to less than B. And just to state the obvious here, one of the things that makes this problem cute is that it is a variant on the knapsack problem. We still have the same knapsack constraint, but the big difference is that we don't have a single objective that we want to optimize. Instead, we have these many kind of mini objectives. Different people have different preferences over what should be included or should not be included in the knapsack. And that means it's much less straightforward to even know what makes a good solution. And this is what I'll be discussing in this talk. This really is the core question of computational social choice. What makes a voting rule good? And there are many possible answers to this question, but the direction of answers that has proven most fruitful in the last years is the direction of proportionality. Proportionality is a rather vague ideal, and because of that, I want to discuss, not define it, but discuss it on an example. This illustration here on the left is supposed to mean that we have a set of agents that cleanly breaks down into two blocks. There's one block, the red block, that makes up for 2/3 of the population, and they're really into sports. The projects that they approve are a ping pong table, a soccer field, a weightlifting station. Whereas the other block is smaller, only 1/3 of the population, the blue block, and they're really into plants. And so they want to fund additional plants for the public park. For simplicity, let's assume that all of these projects cost the same amount, $1, and that our budget is $3. Now, if the outcome that was being chosen was 3 sporty projects, in a sense, that would be very natural. After all, that's what the majority wants. That's how often politics and democracy work. But proportionality says that something is wrong with this, because we have this population here that makes up for 1/3 of the population overall. And if they had 1/3 of the budget, so $1, they could use that $1 to fund something that would make all of them happy. But somehow the outcome completely ignores their preference, and that is unfair. That violates proportionality. Instead, proportionality would suggest that we get to an outcome like this, with 2 red projects and 1 blue project. And this one does feel fair and proportional, because 1/3 of the budget is being spent to make 1/3 of the voters happy, and 2/3 of the budget are being spent to make 2/3 of the voters happy. This ideal of proportionality is what will guide us, but of course, this example doesn't lead us very far, because the discussion in this example really crucially relied on the block structure of approvals here. Whereas in practice, of course, it's not the case that the population cleanly breaks down into multiple blocks that only approve disjoint projects. In practice, the sets of agents who approve a single project might overlap in arbitrary ways. So we'll need to define different axioms that try to get to this ideal of proportionality to different degrees. And indeed, this is what I will discuss in the next few minutes. So I will discuss 3 different axioms of proportionality. The first one is called justified representation, or JR for short. And this will be a very weak axiom. The second one will be a strengthening of this axiom, extended justified representation, or EJR. And this is an axiom that we can still satisfy, but that was a big breakthrough and took some work. And then finally, there's a further strengthening of EJR, which is called core stability, an axiom where we still don't know whether we can satisfy that. And that is one of the major open questions in computational social choice right now. So let's start with the easiest one as a warm-up, justified representation, or JR. This is a lot of text to not animate in, but to show it in one go. But please just follow me along as I will tell you what the different parts mean. Justified representation identifies certain situations where clearly a violation of proportionality has taken place. Just like before, when we had the outcome of 3 red projects, and I argued to you that this was not proportional. So let's suppose that we fix an instance and we fix a specific outcome W. Now, it would be really bad if the following was possible. If there existed some subset of the agents capital S and a project alpha with the following properties, such that namely, every agent I in this coalition S is maximally unhappy with the outcome. They have none of the approved projects in the outcome W. Furthermore, all of the agents in S do approve this project alpha. And finally, alpha is cheap enough that if you take the proportional share of the total budget that belongs to the coalition S according to its size, if you take that proportional share of the budget, that is enough to pay for the project alpha. This is just the equivalent of what we saw before with the blue block of agents. If that was the case, there would be a violation of proportionality. And so we'll call the pair of S and alpha a JR blocking coalition. And we say that the voting rule satisfies the JR axiom if it will never return any outcome W that has a JR blocking coalition. Let me maybe quickly pause here and just check whether the definition is clear. Okay.
So Paul, this is,
Oh, yes.
I should be interpreting this like there shouldn't be a group of people S that can break off and they just get together and fund this project.
Yes, that is a very good, there's a very good intuition that will guide you not just through this axiom, but also the axioms further to come. That is a good definition of proportionality. Thanks. So this axiom of justified representation turns out to be really easy to satisfy. Many of the natural things you might want to do all satisfy justified representation. And in particular, there's an easy greedy algorithm that will satisfy justified representation. Just to be sure, I have copied the definition of a JR blocking coalition up here on the upper right. That's something that I will try to do throughout this talk, just in case you want to glance back, because I do realize that the definition has multiple parts. So in this greedy algorithm, we start with an empty outcome W, and then simply, while there exists some JR blocking coalition with a set of agents S and a project alpha, we add alpha to the outcome W. And we keep repeating this until at some point, there no longer exists a JR blocking coalition, and we return W. The fact that the resulting outcome will satisfy justified representation is nearly by definition, because if there was any blocking coalition, we would not have exited the loop. So all that really remains to be shown here is that these outcomes indeed fit into the knapsack, that we don't overspend our budget. But there's a very simple charging argument here that relies on the fact that whenever we have a JR blocking coalition, then the cost of this project alpha is not too large. And furthermore, there's a very nice property here that says that when we are in the situation that we enter this loop, and an agent I is part of this group, capital S, then from then on in the algorithm, there will be at least one project in the outcome alpha, namely, that I likes, that I approves. And so from then on, because of this third condition here of JR, this agent I cannot be part of any blocking coalition in the future, and this makes this charging argument very easy. And so that is how we can satisfy justified representation without even breaking a sweat. But unfortunately, justified representation does not capture everything that we would want out of proportionality. Let's go back to this example with the red and the blue group, and let's suppose that the outcome is one red item, one red project, and two blue projects. In this case, justified representation is satisfied, which you can see from the previous observation, namely that agents can only be part of a blocking coalition if they don't approve any of the projects in the outcome. And in this case, because every single agent here approves at least one of the projects in the outcome, nobody can be part of a blocking coalition, so justified representation is satisfied. But arguably, there's still something wrong here with proportionality. There's a block here of 2/3 of the voters who, if they had 2/3 of the budget, they could, as what you said, Eric, they could break away, could fund two projects, and all have more than they've been given in the outcome W. So we'll now try to capture this in the stronger axiom, extended justified representation, EJR. And I've just highlighted all the changes here that are relevant. So the one real change that happens here is that now a blocking coalition can no longer only propose a single project alpha, but they can propose an entire set of projects, capital T. Now, of course, we have to make some corresponding changes. Of course, now the proportional share of the budget of S has to not just cover a single project, but it has to be enough to pay for all of the projects in T. Of course, now it's not enough that that a single project is approved by every single agent in S as before, but now every single project in T has to be approved by every single agent in S. But what we get out of this is that now we can make this condition here a bit less restrictive. I is allowed to be part of this blocking coalition, not just if I has zero projects in W that they approve, but it would still be bad if all agents I and S have fewer projects in W that they approve than the number of items in T, because then they would get more after they break away than what they get while staying in the system. So this is how we strengthen the definition. And this turns EJR into an axiom that is no longer obvious to satisfy. I'm running a bit short on time, so I will very quickly breeze over this slide. But long story short, what was clear for a long time was that in a specific subsetting of participatory budgeting, where all the costs are equal, there we knew how to satisfy EJR. And there's a very beautiful, slightly magical potential argument here that was very alluring, but at the same time maybe was a bit of a dead end, because it turns out that fundamentally it can't generalize to the full participatory budgeting setting. So let's instead skip through that slide and directly talk about how to get EJR for participatory budgeting. And the solution for this came from a somewhat unusual direction, namely from some work by a Swedish mathematician called Edvard Fragmén, who wrote this work in 1894 and 1895. And the reason that this was surprising was that this work was only translated quite recently in 2016, when a lot of the work on participatory budgeting was already underway. Fragmén had proposed a voting rule for this more restricted setting of equal costs, but one that happens to generalize very nicely to the setting of participatory budgeting. Let me try to explain to you how this voting rule works. So it works by keeping track of a fictitious bank account for every single voter. Here on the x-axis, we have different voters. And on the y-axis, we have the amount of money that they have left in their bank account. And in the beginning, we just spread the budget equally among all the voters. So everyone receives B divided by N. And now, any time that Fragmén's voting rule buys a new, adds a new project to the outcome, buys a new project, for example, here, this bicycle lane, it will first look at all of the voters who approve this bicycle lane, here 1, 3, 4, and 6. It will look at the cost of this project. It will then distribute this cost among the agents who approve the project, for example, like such. And once it has distributed this cost, it will take that much money from everybody's bank account, and it will add the bicycle lane to the outcome, and it will incrementally build the outcome one by one in that way. So the big question here is, of course, which project do you add next to the outcome, and how do you spread the cost? And the answer that Fragmén gave was that you should always answer both of this twin question from before in such a way that the minimum leftover bank account, amount of funds in a bank account, drops as little as possible. So you're trying to spend money across agents in as continuous, as smooth, as simultaneous a speed as possible. So in particular, so for example, if we now have a different project, if we want to spend the money like that, distribute the money like that over the agents who approve it, then what makes us choose this project and this distribution of the money is that this red line here, the height of the lowest bar after we've paid the money, that this decreases as little as possible. But it turns out that this voting rule actually does not satisfy EJR, even in the restricted subsetting of multi-winning elections. And because of that, for example, I did not pay enough attention to this voting rule at the time, and this potential argument to me seemed much more promising, and this is what I was thinking about at the time. But then it turns out that Dominic Peters and Piotr Skowron figured out a variant of Fragmén's voting rule that just answers this twin question of which project to prioritize and at which distribution of prices. They answered that a bit differently, and that turns out to guarantee EJR and participatory budgeting. So their answer is that what you should minimize is always the largest payment. So you don't really care about whether people have already spent a lot of money before or have not spent a lot of money before. You should always try to just spread the payment for the next project as evenly as possible. And that will give you a different way to decide which project to add to the outcome next. It turns out that this voting rule, which they call the method of equal shares, does satisfy EJR. And this voting rule not only satisfies EJR, but is also polynomial time. So this is something that was not at all that people were able to achieve in the restricted subsetting, but only in rather convoluted and tricky ways. This is very natural here. And it is also a very commonsensical method to decide which projects to fund. And these three properties together actually make it quite attractive for use in practice. And this is what we're seeing right now. So this work is still pretty recent, but 2 cities, one in Switzerland and one in Poland, have just or are just going to use the method of equal shares for their participatory budgeting. So now for the final part that I want to talk about in participatory budgeting is I want to strengthen the axiom even more from extended justified representation to what we'll call core stability. And core stability really gets to this intuition that you, Eric, had of breaking away and using money for their own good. It gets rid of the second assumption here that I personally, for example, never liked. The second assumption says that the group capital S is only allowed to propose the set of projects capital T if every single person in S likes every single project in T. But why is it not natural to say, no, they can propose any set of projects that they can afford? And the benchmark is that the benchmark for a violation of proportionality is if every single agent in the coalition S will have strictly more projects that they approve in this counterproposal capital T than they were given in the outcome W. So this is a strict strengthening of extended justified representation. And again, we say that the voting rule satisfies coercibility if it does not admit any of these blocking coalitions. And this is now a really hard open question. We do not know whether existentially there always exist outcomes that are core stable, and we have no idea what kind of algorithms will be able to give that to us. We have some partial progress to report on that front. So one kind of very important work is by Kamesh Munagala and co-authors. I think I saw Kangning earlier in the call. He's one of the co-authors, unless I'm mistaken. And they've done really good work on approximating core stability. So on the right here, I'm changing again slightly the definition of a core blocking coalition, where really crucially, I'm now adding this factor here, which says that the coalition S is only about to complain about a lack of proportionality if the counterproposal that they have makes everybody 9.27 times more, gives them 9.27 times more projects that they approve than the outcome W. So this makes the axiom weaker and more satisfiable. And they do prove that outcomes always exist that satisfy the 9.27 core. And they do say that they have a polynomial time voting rule that satisfies a somewhat weaker approximation ratio for core stability. So this is one approach. And well, the constants here are large enough to probably suggest that more work can be done, and that even in an approximation regime, you can get closer to core stability than we are right now. The only other, the other piece of progress that we can talk about is guaranteeing core stability in subsettings of participatory budgeting. And there, the main situation is still pretty pessimistic, namely, even in this subsetting that I mentioned before of multi-winner elections, where all the costs are equal to 1, it's a big open problem whether core stability can be guaranteed and what algorithms could be good for that. But if you further restrict the setting to still assume that all the costs are equal to 1, but in addition, you allow the outcomes to choose multi-set of projects, to choose a really popular project multiple times if it exists, then a paper that I've been involved in together with Marcus Brill and other co-authors, there we show that core stable allocations do indeed exist, but the methods that we use to prove this, again, rely on a kind of potential argument that we know does not carry over to participatory budgeting. So how to make progress even on this problem here is also an open problem. This is what I want to say on participatory budgeting. And I now want to enter the second part of this talk on selecting representative panels. The picture here on the left was chosen because these people here are chosen so that their overall composition in terms of racial groups, gender, age, and so forth is all representative of the US population. As a motivating example, suppose entirely hypothetically that there's a hypothetical online seminar that you're in charge of. And suppose that you need to choose 16 speakers for the different slots that you have over the year. You can choose these speakers from a pretty large pool of potential speakers, but you're constrained in your choices in different ways. So for example, there are different sub-communities of your discipline, and X, Y, and Z, and for each of them, you want to have at least one speaker. This might be one restriction. Maybe you want to have a balance of different levels of seniority. Maybe you want roughly a third of your speakers to be tenured, a third to be a tenure track, and a third to be before the tenure track. Maybe you want some geographic balance between North America, Europe, and other parts of the world. Maybe you don't want everybody to just be male speakers, and so forth. All of these constraints, I think, are probably familiar to you. So building algorithms that can find these representative panels of a fixed number of people who satisfy all of these different demographic or other group quotas, that is what this part of the talk will be about. And one of the things that I should warn you about is that this part of the talk is a bit different. The work that I'm summarizing in this part of the talk is a bit different from the work that I've been summarizing before. In my mind, the work on participatory budgeting is pre-structured. It reminds me of these trees here, where some of the work is happening in parallel, but much of the work is building up on each other, going into a common direction. And my inner picture for the work on representative panels is much more like this tree here, these two trees here. So it's not that people have been trying to work on this problem to make progress in a single direction, but they've actually come from different directions. They've been trying to solve different problems in computational social choice and have encountered representative panels as a common bottleneck that they've all struggled with, all found solutions to. But I think that makes it really attractive to reconsider this element of representative panels, because if we can improve that, then a lot of other tasks downstream will profit from that. Again, let me introduce some notation. So let's say that we have a set capital F of features. Those features might, for example, be seniority, geography, gender, and so forth. And for each feature in the set capital F, there is a set VF of values. So for example, the feature seniority has a set of values, tenured, tenure track, postdoc, and hopefully some others. We have a set of agents, capital N, and every agent I and N for every feature F has a certain value for that feature. And by some abusive notation, but this is the only way that I know to avoid a lot of indices, I will write this as F of I. So for example, the feature seniority applied to the agent Paul will be equal to postdoc. We have a desired size that we want our panel to have, which is an integer. Before that, in the example before that was K. Sorry, in the example before that was 16. And then finally, for every combination of a feature and a corresponding value, we have a lower and an upper quota, LFV and UFV. So for example, for the feature and the value for the feature seniority and the value postdoc, there would be a lower quota on how many postdocs we should choose in our panel and an upper quota for how many postdocs we should choose in our panel. And this is indeed the problem that the algorithm should solve. The algorithm's goal is to choose a subset of the agents, namely K many of them, such that for any feature and corresponding value, F and V, the number of people on the panel in S who have this value for this feature should lie between the lower quota and the upper quota. Let me again quickly pause in case somebody, in case something is unclear. Okay. So as I said, a lot of different papers have come across this problem, and we have rediscovered a couple of times some pre-clear structure to this problem. And the landscape overall is as follows. If the number of features is 1 or 2, then things are really nicely structured. There's a very clear combinatorial structure. And for example, this is exemplified by the fact that deciding whether your set of quotas is feasible, where there are indeed panels that satisfy all these representativeness quotas, is an efficiently solvable problem. Specifically, if you, it's very natural to write the question of, to write the search for a representative panel as an integer linear program. And when you take the fractional linear program relaxation, this linear programming relaxation is totally unimodular, as for example, Robert Brederick et al. Proved, which means that you can use this linear program, solve it in polynomial time, and you will immediately have your solution. You will immediately have a panel. You will immediately know whether a panel exists or not. So everything here is very structured. Unfortunately, the structure does break down as soon as the number of features is 3 or more. In that case, feasibility is NP hard, and that is just a symptom of things just becoming much more combinatorial. There are some natural ways that you might hope to get around that by nice approximations, but that doesn't work. Multiple groups, again, Robert Brederick, I think, were the first ones, but for example, we've also tried that to think about this in an FPT way, a fixed parameter tractable way. And it is true that this problem is fixed parameter tractable if you parameterize by the total number of values that you have across all features, but only through an algorithm that's not very interesting. Specifically, integer linear programming in this case is fixed parameter retractable, but the algorithm that proves this is completely impractical and really slow. So because typically we do care about features that are more than 3, we have looked at different approximate versions. And approximate versions here means algorithms that will not be able to always guarantee to satisfy all the quotas, to always be between the lower quota and the upper quota, but that sometimes we'll have to lie outside of them, but we want to lie outside in a bounded manner, not too bad. And I'm trying to illustrate this here on the left. So I've chosen here 3 combinations of features and corresponding values, FV, F prime, V prime, F double prime, V double prime. And for each of them, from left to right, this axis is supposed to symbolize how many among our panel members have this feature value combination, say, for example, FV. The green range here is always between the lower quota and the upper quota. So this is what we would love to fall into, but sometimes we will not be able to guarantee that. The different work in computational social choice on this problem of finding representative panels has followed 3 different algorithmic approaches here. One approach is by Jérôme Lang and Piotr Skowron in 2018, which uses a local search algorithm that locally tries to get, through a local search, tries to get as close to these quotas as possible. And specifically, they say that if a panel, so suppose that this is a panel here, and the little triangles indicate how many people really from every feature value combination we do have on our panel. So for this feature value combination here, everything is great. We are indeed within the quotas that we wanted to, but here we exceed the upper quota, and here we fall short of the lower quota. Lang and Jérôme and Piotr, they define the violation of these quotas by simply adding up all of these differences between the closest quota and where your representation for the feature value actually is. And what they show is that if the objective is to minimize the sum of these red regions, then their algorithm will be optimal within an additive k times the number of features. And to my knowledge, this result is not obvious. I don't have like an obvious intuition that would point towards that. But at the same time, it is a pretty loose bound. For example, it might say that for every single feature, you have one value that you're completely, where you're completely unrepresentative. You wanted to have 0 of them, and everyone belongs to them. So this is a very loose bound. The other 2 approaches use the rounding of fractional solutions. So they will first solve, for example, the linear programming relaxation that I talked about before. And they will then try to round that. They will assume that there's a linear programming relaxation that lies within all of these quotas. But this might now not be an actual panel. It might fractionally choose some people, even though we, of course, have to make a binary decision about whether Eric is on our panel or whether he isn't on the panel. And the most simple approach that you could take, that was taken, for example, by Sellers et al. And by Bay et al., is randomized rounding, where once you have your fractional solution, you randomly flip coins to decide whether people are in the panel or not. And what that will give you, it will give you a guarantee for every single feature value on its own, namely that you will not violate the quota by a magnitude of more than order of square root of the actual quota that you're violating times the logarithm of the total number of values summed up over the features. This is just what you get out by using concentration and a standard union bound. And this is one of the tools that we have, but again, it is a relatively loose bound. And then the final approach that we have uses discrepancy theory, and specifically the Beck-Fiala theorem. It again assumes that there is some fractional solution that fits inside all of these quota ranges. And then it shows that for every feature, you don't have to violate this feature by more than an amount that's essentially the number of features. And that, again, unfortunately, is still pretty loose. So all of these are technical lemmas, but I think what is much more impressive are not these technical lemmas, but how much use we've been able to make of these kinds of results for other tasks. So this task of finding representative panels has come up in many settings. There are some papers that have studied it standalone. But for example, Elisa Seles and Robert Bredick et al., they've looked at multi-winner election settings where there is an electorate somewhere out there, they voted for different candidates. And so you want to find, say, the city council that most closely matches who people want to see on the city council, but at the same time has to satisfy certain quotas. For example, it has to have a gender balance and a balance around people, representatives from the different districts in the city. So this is one of the things that they've done with it. This work by Simbrano et al. Looks at a slightly different problem, but one that turns out to be technically very closely related. they use it for multidimensional apportionment. So they're trying to say, well, for example, in the country of Chile, if you fill your legislature with members of different parties, how many seats should every party get? And then furthermore, what are the quotas that should be imposed on these parties, where they then have to choose that many women, that many men from their ranks, that many people from every single region within the country. So this is a form of multidimensional apportionment, which is what they're doing with that. Outside of research, just in pure practice, I've solved this problem in practice sometimes when helping a nonprofit that I talk to from time to time, where they wanted to build focus groups and they wanted to screen a documentary to them, and they wanted to see that this documentary actually appeals not just to, say, the kinds of people you can find on the college campus by recruiting them with a flyer and promises of pizza, but actually a diverse audience. And so they've wanted to build focus groups in very much this way. And then finally, a topic that is very close to my heart in particular is a domain known as citizens' assemblies. And both of these papers here are joint work with my collaborators, Flanagan et al. I do have a tiny bit of time to very quickly talk about citizens' assemblies since they're close to my heart. So what we do there is not just find a single representative panel, but we actually optimize over the space of all probability distributions over representative panels. And of course, in general, there can be many of them. So for example, suppose that we have two representative panels here containing these 4 agents each, and we have a probability distribution that chooses the first panel with probability 2/3 and the second panel with probability 1/3. In this case, this probability distribution is fairly unfair. So this probability distribution over representative panels is unfair in the following way, that namely, the red agent will be contained in an output drawn from this distribution with probability 1, but the orange agent, by contrast, will only be contained in this panel randomly chosen with probability 1/3. So there's a clear inequality here. However, we could, for example, add another representative panel to the mix, this panel here, and we can choose each of these panels with probability of 1/3. And in that case, it will turn out that every single agent that we have will be in the randomly chosen output with a probability of 2/3. And in these papers, what we're doing is we are finding the probability distribution that makes these probabilities of inclusion as close to equal as possible. And when technically phrased like that, that might strike you as a strange and esoteric question. But it turns out that this is a very practical question. There are people out there doing so-called citizens' assemblies, which are doing exactly this. And so, for example, the algorithm that we've developed is now actually implemented and has been used in Scotland for a random set of citizens to debate climate change. In the United Kingdom, the government's test and trace strategy was overseen by, again, a body of randomly selected citizens who were chosen with our algorithm. And right now, there's a citizens' assembly in Germany coming up that has been convened by the German legislature, the Bundestag, that again will be chosen using our algorithm with an optimal probability distribution over representative panels. To now come back to representative panels more general, the one thing that really bothers me about the state of research here is that I think that none of our bounds are too pessimistic, and none of them are tied to the level that we would need. So from my experience in practice, the gaps between the lower and upper quotas are often really tight. Often there's not a gap at all. Often these quotas are equal, or maybe there's a gap of 1 or 2, and that is much less than any of these bounds here can provide. And the practitioners choose these really tight gaps because they're confident, based on their experience, that they will be able to find panels, even with pre-crude heuristics, that satisfy all these very tight and constraining quotas. So somehow theory, I hope, can catch up with that and can identify, for example, properties about the way that features and feature values are distributed in the population that say that if that quantity is high, then we should be able to get much closer bounds in terms of the quota violation than, say, the order of F or the order of the magnitude of the quotas. Okay, let me conclude here. In this talk, I talked about 2 different domains. The first one, participatory budgeting. The second one, representative panels. In participatory budgeting, we looked at different definitions of proportionality that increased in stringency. The easiest one was justified representation, which was easy to satisfy with a greedy rule. The second one was extended justified representation, which was much harder, but which finally with the method of equal shares, we now know how to guarantee this in participatory budgeting in polynomial time. And there's one axiom where we're still hoping to make the checkmark in the future. It's still an entirely open question how to guarantee this or even prove its impossibility. And we would love some help from the TCS community in this. The second domain was representative panels. There, the situation is we're kind of stuck. There is an NP hardness and a combinatorial structure that the field hasn't really made enough progress on yet in characterizing and bounding how much loss we really have to accept versus how close we can get to the quotas. Different approximate algorithms have been proposed, but all of these bounds are still fairly pessimistic. And there are many downstream applications that could really profit from more granular results and from more optimistic results. So again, this is an explicit invitation for you all to think about that. And I would love to chat about this. Let me leave it at that. Thank you so much for your attention. And I look forward to any questions and to discussing with you.
For the representative panels problem,
Yeah.
the results that you were mentioning about deciding the feasibility, is
Yes.
it talking about fractional feasibility or integer feasibility?
It is talking about integer feasibility. And yes, you're entirely right, because fractional feasibility, of course, you can test with a linear program. But integer feasibility turns out to be something that's quite, that adds sorry.
Okay, so fractional feasibility is completely determinable no matter what is the number of factors, right?
Yes, yes.
Okay, thank you.
Thank you.
Are there any other questions?
Yeah, maybe. I have a question on the method of equal shares.
Yes.
And I think it's a pattern that happens quite often in any algorithms for democracy, that you could have basically people deciding to make a smart vote. For example, if you have, if you know a lot of people are interested in a project you also like, you could decide to not vote for it and kind of save your budget, at least for the two rules you've shown.
Yes.
And is there like maybe any rule that can circumvent this problem, or is it just always going to happen?
There are unfortunately really strong negative results. What you're referring to, I would call strategic voting or incentive compatibility. And ideally, you would want something where revealing exactly the projects that you care about will always be in your best interest, and holding back is never in your interest. But you're right, you can totally manipulate in these voting rules that I've shown. And there's a result by Dominic Peters that shows that even for a very, very, very weak form of proportionality and a very weak form of strategy proofness, you will never be able to avoid this.
Okay,
thank you. And unfortunately, I should say, this is a very common situation in computational social choice. So really, far at the roots of social choice theory is a very famous result by Gibbet and Satterthwaite that proves that even in the classical voting setting, these manipulations are hardly possible to rule out as long as you want anything good from your voting rule.
A long time ago, for the congressional apportionment problem, there was a randomized rounding solution by Knuth. Is it related to the second problem that you were talking about?
I'm very interested in that.
Okay.
I don't know the reference I think that you're talking about. There are some loose connections between classical one-dimensional apportionment. Well, no, this is unfair. They are not loose connections. So the setting of finding representative panels, if there is only one feature in a very real sense, is just apportionment theory. And you could do that in a randomized way, where it has been studied. You could do that in a deterministic way, where it has been studied even more. I have actually done some work on randomized apportionment just recently at EC. I would love to hear more about that reference, because I think it's not the reference that I typically think of. Okay, maybe you can just put it in the chat.
I don't have it handy, but I can dig it out and send it to you.
I would appreciate that.
There's also a question in the chat by Alexander Kasachkov. who's asking whether you can relax the size of the panel in the representative panel setting.
Yeah, so this does not get you around the problems, at least fundamentally. I don't know the exactly tight results. Let me find. I think Elisa Celis et al., I think their paper tries that. And I think the paper by Bay et al., actually, that is the core of their model, that they have some slack in how large their panel is. And they still run into the same computational hardness. Thanks.
Cool. Okay, so I'll take us off the recording, but we can stick around and ask all questions.